Hi everyone, my name is Clarice A Diebold. I am a PhD candidate at Johns Hopkins University, and today I will be talking about echolocating bats, Eptesicus fuscus, track auditory object motion. While most predators primarily use continuous visual information to navigate, the echolocating bat emits ultrasonic vocalizations and uses information from returning echoes that bounce off of objects in their environment to navigate three-dimensional space. Bats can dynamically modify the spectral temporal parameters of their calls as they approach their targets. Bats must often navigate dense forests while tracking evasively flying insects, a task that requires specialized strategies to use discontinuous acoustic cues to successfully intercept these targets. While in cluttered environments, bats must further contend with the temporal gaps in new sensory information about the position of their target. Recently, we found that bats use predictive strategies when tracking moving targets while perched on a platform. Bats consistently orient their head ahead of target motion, using a combination of velocity estimation and a fixed head angle correction to anticipate the future position of their target. Further, when the target's path was temporarily occluded and no new sensory information could return to the bat, they still maintained anticipatory head motion behavior, but did not increase their call rate in the same way that they did in unoccluded conditions. This suggests that when no new sensory information returns to the bat relies instead on internal models of target motion rather than receiving new sensory information from the echolocation calls. To further investigate the limits of predictive tracking, we introduced new occlusion and trajectory conditions to our previous experimental paradigm, where we trained bats to perch on a platform and observe a target move across their acoustic field. We introduced a back-and-forth trajectory condition, which tested the bat's ability to track a target that violated expectation by changing directions during trial. We also introduced small and large-sized occluders. These trajectory and occlusion conditions test the limits of the predictive model and what sensory information is necessary to maintain accurate tracking. In the back-and-forth trajectory condition, we found that when target motion deviated from the expected trajectory, the bat's head position did accumulate some error. However, the bat was able to recover from this and resume successful tracking, though a bit behind the target's motion. Call rate increases slightly after this change in motion, suggesting that the bat may be taking in more sensory information. Preliminary results of the different-sized occluder condition showed that the small occluder functioned similarly to the medium-sized occluder from the previous experiment, where the bat was able to successfully maintain predictive internal representations of target motion. However, in the large occluder condition, there seems to be an accumulation of error or an alternative strategy where instead of maintaining a representation of target motion, the bat is attempting to skip the occluder and only resumes anticipatory tracking when new sensory information is available and the target emerges from the other side of the occluder. So in summary, bats employ internal models to predict target motion in relatively simple trajectory conditions, and we added complexity to target motion across two different axes, clutter and erratic flight, which showed that there is a limit to the reliance on prediction before internal models need to be updated with new sensory information. So increased complexity demands new sensory information for prey interception. Thank you very much for listening.